Section 1 Introduction. In this paper, we're introducing a concept that brings forth improvements in the field of large language models, or LMs. LMs have proven to be powerful tools across various sectors. However, they come with a downside: the huge computational expense resulting from the need to store vast amounts of information and to keep up with growing context lengths. As these lengths expand, they allow access to more distant data, but they also increase the complexity of the system. One solution to this issue is the Retrieval-Augmented Language Modeling, or RALM. This model uses a method of precise data retrieval to reduce the memory and computational demands. Plus, RALM can improve factuality, relevance, and generalization without requiring further training. This can be achieved by merely changing the retrieval index. But the problem with previous RALM models is that they didn't give the data retriever, the tool that fetches the required data, the same importance as the LM during training. Sometimes, the retriever was only used during testing or remained unchanged during training, which stopped it from evolving along with the LM generator. At other times, the retriever was trained jointly with the LM, but only after they both went through a separate pre-training phase. We aim to address this with our new model called Retrieval-Pretrained Transformer, or RPT. This model gives equal importance to the retriever and the LM, training them together right from the beginning. The RPT uses a unique method where the retriever uses the LM's information to make calculations, and the retrieved data is integrated back into the LM to make word predictions. We also introduce a special loss function to train the retriever to fetch data chunks that will most likely help generate subsequent text. Our focus is on modeling extensive documents like books, articles, codes, scripts, and dialogues. This kind of content often requires a massive index that can be stored in memory during a forward pass. When tested on 4 language modeling tasks, the RPT showed lower perplexity across all tasks, outperforming previous models and strong baselines. We also noticed that RPT retrieves high-quality data chunks compared to other retrievers that rely on lexical data. In conclusion, our research shows that the RPT can be a stepping stone towards the next generation of pre-trained LMs where the retriever is given significant importance in both architecture and the training process. Section Summary. The success of large language models, LMs, comes at a computational cost due to increasing parameter counts and growing context lengths. Retrieval-Augmented Language Modeling, RALM, can reduce memory and computation requirements by precisely retrieving relevant information. In this work, the Retrieval-Pretrained Transformer, RPT, is presented, which trains a retriever from scratch jointly with the LM, and relies on self-retrieval and an auxiliary loss function to fuse retrieved representations back into the LM decoder for making next word predictions. RPT improves perplexity across all tasks and retrieves high-quality chunks compared to retrievers that rely on lexical information, paving the way toward the next generation of pre-trained LMs. Section 2 Background. To provide context for our research, we will first examine some related studies in the field of Retrieval-Augmented Language Models, RALMs. We will then explain how our work expands on these studies in the following sections. Earlier research in the RALM field, like KNN-LM, used a technique called retrieval to enhance language models. This technique combines the prediction for the next word generated by the language model with a suggestion provided by a retrieval mechanism that only operates during testing. A subsequent model called Chunked Cross-Attention, CCA, introduced retrieval at the training stage as well. This method deeply integrates the retrieved representations into the transformer decoder's representations via an attention mechanism. However, there was a limitation in that the retriever was trained separately and remained unaltered during training. This restricted its adaptability to the language model throughout the training process. Our study, similar to a model known as TRIME, develops a retrieval-augmented language model from scratch, where both the retriever component and the decoder language model are trained together. However, our approach varies from TRIME in 2 key ways. Firstly, TRIME, like the KNN-LM, integrates information from the retriever in a shallow way, using distribution interpolation. In contrast, we use CCA for a more profound fusion process. Secondly, TRIME utilizes lexical cues to guide the retriever. This means, given a query, TRIME's retriever learns to retrieve contexts that result in the production of the same token as the query. We take a different approach. We use a scoring language model to assess which text sections are relevant for increasing the chance of generating that chunk. This leads to a more semantically focused retrieval. This method is similar to one used in a model called EPR, which employs this concept for learning to retrieve prompts for in-context learning, and in a process called perplexity distillation, used in a model called Atlas. However, Atlas doesn't train the retriever and language model from scratch and is more suited to knowledge-intensive tasks because it operates as an encoder-decoder model. Unlike Atlas, we train our model from scratch and use a decoder model, which is more suitable for handling long texts. Section Summary. The section reviews recent work on Retrieval-Augmented Language Models, RALMs, starting with KNNLM and extending to Chunked Cross-Attention, CCA, and TRIME. While TRIME and this work both train the retriever and decoder LM jointly, this work differs in its use of a scoring LM to evaluate relevant text chunks for retrieval, leading to more semantic retrieval, and in its use of CCA as a deeper fusion mechanism. Additionally, Atlas does not train the retriever and LM from scratch and is an encoder-decoder model, while this work trains from scratch and uses a decoder model suitable for long texts. Section 3. Retrieval-Pretrained Transformer. In this section, we discuss a special transformer model, known as the Retrieval-Pretrained Transformer or RPT. This model works similarly to Retro, another type of language model that uses chunk-wise retrieval. Here's how it works. Imagine we're given a series of input tokens. Let's call the total number of these tokens L. We then divide this series into several non-overlapping parts, each of equal length, M. These parts are what we refer to as chunks. So, if you have L tokens and each chunk is M tokens long, you'll end up with L divided by M chunks. Now, the interesting part begins. For each chunk that could be a query, the model retrieves a subset of no more than K times L divided by M chunks. It's important to note here that we only retrieve chunks that can be retrieved. This means excluding a certain number, W, of chunks which the model can already access via causal self-attention. So, what's the goal here? It's to train a model that picks out a subset of chunks that makes it more likely to generate the next target chunk in an autoregressive manner. In simpler terms, our model tries to choose the best chunks to help predict what comes next in the sequence. We present our method in two major sections. First, we delve into the architecture of our model. It capitalizes on causal cross-attention, CCA, to merge retrieved representations into the language model while also introducing a learned retriever component. Next, we discuss the training method. In this part, we train our retriever to pick out chunks that are beneficial for generating a future chunk, based on a reference language model. Section Summary. The Retrieval-Pretrained Transformer, RPT, is a model that retrieves a subset of chunks for a given query chunk to increase the probability of generating the target chunk in an autoregressive manner. The input sequence is divided into non-overlapping chunks, and retrieval is performed at the chunk level. The model architecture includes a learned retriever component and CCA to fuse retrieved representations into the LM, and the retriever is trained to retrieve chunks useful for generating a future chunk according to a reference LM. Section 3.1 Model Architecture. In this section, we are going to walk you through our model's architecture, which is illustrated in Figure 3.1. Our model processes input that is broken down into 45 tokens. These tokens are further divided into 9 separate sections, or chunks. To process this information, we utilize a technique known as causal self-attention, which we apply to 3 chunks at a time, or a total of 15 tokens. This architecture can be split into 2 main components. On the left, we have the decoder stack, also referred to as the reader. On the right side, we have the retriever. Let's break this down further. The reader component of our model is divided into 2 separate parts. The bottom half consists of standard transformer decoder layers. These layers take in our chunks as input and output representations. These output representations are then used by the retriever component and the top decoder layers. The top half of the reader, or the upper decoder, applies a technique known as chunked cross-attention, CCA. This process is crucial for integrating information from the most relevant chunks, the top K neighbor chunks, that were retrieved by the retriever component, back into the language model. We apply the standard CCA layers as done in the retro model. Here, for each one of the smaller divisions in the chunks, we have something known as queries, which are the token representations of that specific chunk. These are output by the causal attention mechanism. The keys and values, on the other hand, are the token representations for the top K neighbor chunks, which are output by the retriever. If you'd like a more in-depth look at how CCA works, we'd recommend checking out the retro paper. Now, let's discuss the retriever component of our model. This component also includes a mechanism we've called a neighbor gating mechanism. This mechanism is responsible for controlling the impact of the retrieved representations on the final output. Section Summary. The model architecture consists of a decoder stack and a retriever. The decoder stack is divided into 2 parts, with the lower decoder being standard transformer decoder layers and the upper decoder using chunked cross-attention, CCA, to fuse information from the top K neighbor chunks retrieved by the retriever back into the LM. The retriever component uses standard CCA layers from Retro, and a neighbor gating mechanism is used to modulate the effect of retrieved representations. Section: Retriever. We introduce a component called the retriever. This retriever operates on the outputs created by the lower decoder, generating a similarity score for each pair of data chunks. Let's visualize a chunk of data as a question, symbolized as C(Q). The retriever then assigns a score to every other chunk of data, let's call it C, by comparing it to this query chunk. This score calculation involves learned linear projections represented as W_Q and W_K. The retriever also calculates representations of chunks. It does so for a chunk C, which contains m number of tokens, by applying bidirectional attention over all the tokens in the chunk and then averaging the results over time. This process respects causality, as these representations are only utilized when predicting the next data chunk. The retriever then identifies the top k scoring chunks for each query chunk. These are termed the neighboring chunks. For every neighboring chunk, we append the representation of the following chunk to provide extra context. We then compile all these enriched representations into a tensor for use in subsequent steps. Like the retro system, we also enhance the representations of the retrieved chunks using a process known as cross-attention, performed over the tokens of the query chunk. It's worth highlighting that our retriever is fully incorporated into the language model. In contrast to methods like TRIME and KNNLM, the lower decoder computes representations for the retriever, which we refer to as self-retrieval, and the upper decoder uses the representations produced by the retriever. Section summary. The retriever takes in chunk representations from the lower decoder and calculates a similarity score for each pair of chunks. The retrieved neighbor chunks for each query chunk consist of its top k highest scoring retrievable chunks, and their representations are concatenated with the succeeding chunk's representation to provide additional context. The retriever is an integral part of the LM, where the lower decoder computes representations for the retriever and the upper decoder consumes representations produced by the retriever. Section: Neighbor gating. We've introduced a mechanism called neighbor gating, which helps us choose the most useful aspects of neighboring data points when blending them into a higher level analysis. This can be understood by picturing a series of data points or chunks of information that we're looking to analyze. For each chunk, we have multiple neighboring chunks. Suppose that chunk C has a neighboring chunk that we'll label K. We describe each K neighbor using what we call token representations, which can be thought of as the unique set of features for each neighbor. This is represented as a 2 meters by d dimensional matrix, where m represents the time dimension and d, the feature dimension, denoted as C_I_K. In order to simplify these token representations, we take the average across the time dimension. This results in a single vector for each neighbor, reducing our 2 meters by d matrix to a single dimension, denoted as C_I_K. Next, we enhance each neighbor's representation by applying what's called causal attention. This means that each neighbor only considers the chunks that came before it, or other neighboring chunks that rank higher. This is important because it mimics the way cause and effect works in the real world. The past influences the present. Once we've enhanced these representations with causal attention, we can adjust them with a gating score. The gating score is obtained by applying a sigmoid activation function, which outputs a value between 0 and 1, to the dot product of a learned parameter vector and the enriched representation, divided by the feature dimension, d. To ensure the gradients keep flowing during the optimization process, we don't let the gating score drop below a small value, which is set to 0.1 in our experiments. The result of this multiplication gives us what we call the gated retrieved representation, denoted as C_I_K_G. To summarize, the neighbor gating mechanism refines the neighbor representations, taking into account their relevance and sequence, and adjusts their contribution using a gating score. These gated representations are then used as inputs, or keys and values, when we perform a certain type of analysis known as canonical correlation analysis, CCA, in the upper decoder. Section summary. The paper proposes a neighbor gating mechanism to select useful neighbor representations for fusing into the upper decoder. The mechanism involves mean pooling across the time dimension to obtain a vector for each neighbor chunk, applying causal attention to enrich the neighbor representation, and obtaining the gated retrieved representation by multiplying the augmented representations by a gating score. In the upper decoder, CCA is performed using the gated retrieved representations as keys and values. Section 3.2 Supervision Signal. In Section 3.2, titled Supervision Signal, we are exploring the task of determining adjacent chunks of data, or neighbor chunks, that can assist in generating the next chunk in the sequence. These chosen neighbor chunks serve as a supervision signal for our retrieval mechanism. In essence, we want to find chunks that would be useful for generating the next chunk. The method we use is somewhat similar to existing approaches, but with a twist. While others might use only lexical clues, we go a step further and employ an independent scoring language model, LM, to assist in the task. However, there is a computational challenge we must address: scoring every chunk in relation to all preceding chunks. This process is quadratic, which means it becomes increasingly difficult as the number of chunks increases. To circumvent this, we employ a straightforward unsupervised retriever called BM25, which processes the combined current and next chunks and produces a set of candidate neighbor chunks. These candidates are the chunks that have a high lexical overlap with the current and next chunks. Interestingly, our retriever has access to the tokens that need to be generated by the language model. Although this may sound unusual, it's perfectly fine during the training phase. Our scoring function, derived from an independently trained language model, assigns a score to each candidate chunk. This score is based on the likelihood that the information in the candidate chunk is more useful for decoding the next chunk compared to chunks that are close to the current chunk. To illustrate, imagine a situation where you have a candidate chunk and two preceding chunks. If the candidate chunk's information is more useful for generating the next chunk than the preceding chunks, the score will be positive. We then apply this scoring function to all chunks and create a set of positive chunks for each current chunk. This set includes candidates with positive scores, indicating that these chunks should be beneficial as they are at least as good as the local context. Armed with this ordered list of positive chunks, we can apply standard retrieval training methods to further enhance our model's performance. Section summary. To generate the next chunk in a query, the authors identify neighbor chunks that can be used as supervision signals for the retriever. They use a BM25 unsupervised retriever to return a set of candidate neighbor chunks with high lexical overlap with the current and subsequent chunk. They then compute a target-based score for each candidate chunk to determine whether the information in the chunk is more useful for decoding the next chunk compared to information in the preceding two chunks. Section 3.3 Training. In Section 3.3, we discuss the training process. To hone the parameters of our retrieval component, we've used an adaptation of the popular lambda rank loss method. Essentially, for each query chunk, we calculate a loss. Let's break it down. A chunk from the query is symbolized by C(Q), and its loss calculation involves a sum. This sum takes into account every pair of candidate chunks where one candidate chunk, represented by bar C_L, is among the positively ranked retrievable chunks for the query, and its score, represented by S%_T, bar C_L, is greater than the score of the other candidate chunk, represented by bar C_J. This sum is calculated by applying a certain function to these pairs of candidate chunks. This function calculates the difference in scores between the two chunks and then subtracts a margin hyperparameter, denoted as tau, from it. If the result is less than 0, it is changed to 0. This number is then multiplied by a scaling factor lambda_JL, which is derived from the lambda rank and takes into account the relative ranking of each candidate. A loss is incurred when, for a particular pair of candidate chunks, the ranking based on their respective scores disagrees with the ranking based on the query's score, by a margin of at least tau. By optimizing this loss function, our model, RPT, can differentiate between chunks that are relevant and those that are not. The final loss calculation is a combination of two elements: the standard language model loss, represented by L_text LM, and a component proportional to the retrieval loss, represented by alpha_text ret L_text ret. The coefficient of retrieval loss, alpha_text ret, is increased progressively during the initial 100,000 steps of the training. In the same vein, the margin hyperparameter, tau, is also increased gradually during the training process. Section summary. To train the retriever component, the lambda rank loss is used, which considers the relative ranking of each candidate. The loss is non-zero when the target-based score disagrees with the ranking of the query-based score for candidates in R_text pos_Q. The final loss is a combination of the standard LM loss and the retrieval loss, with the retrieval loss coefficient increasing linearly in the first 100K steps and tau increasing linearly during training. Section Scheduled Sampling. To make sure the model we train aligns better with what it'll encounter during real-world applications, we introduce a technique called scheduled sampling. After identifying the top K similar sections or chunks, we select them with a probability of 1-P_text SS, and with a probability of P_text SS, we select the top K scoring candidates from R_text pos_Q to input into our canonical correlation analysis, CCA. We tweak p_text ss from 1 to 0 during the initial 90% of training, using what we call a cosine schedule. This approach enables the model to gradually adjust and start making use of its own predictions. We'll discuss the effects of this strategy in a later section. We've also employed a sliding window attention mechanism during both training and the model's use or inference. As previously mentioned, our decoder processes W chunks at a time, with each chunk containing M elements, and applies what's known as causal attention over them. In real terms, to ensure that the initial elements can refer back to previous ones, we use a sliding window technique. This process involves a window size of 2048 tokens and a step size, or stride, of 1024 tokens. As a result, each window's input consists of 2048 tokens, and the outputs are the representations of the last 1024 tokens. These outputs incorporate the keys and values of the preceding 1024 tokens for better contextual understanding. During the model's actual use or inference, we implement a similar process. We calculate and store the key and value representations for segments of 1024 tokens. We then use these stored values as context for predicting or calculating the likelihood of the next segment. Unsurprisingly, during inference, the retrieval component of our model can access all tokens from the document's beginning. Section summary. During training, scheduled sampling is applied to reduce train-test mismatch by gradually teaching the model to use its own predictions. The sliding window attention mechanism is used to give the first tokens access to past tokens, where the input to each window is 2048 tokens and the output are the representations for the last 1024 tokens. At inference time, a similar procedure is applied, where the key and value representations for segments of 1024 tokens are computed and cached, and then used as context for generating or estimating the probability of the next segment. Section. Additional details. We use training sequences that are 16,384 tokens long, divided across 4 devices, each handling 4,096 tokens. The decoder stack processes 2048 tokens at a time, following a sliding window method, breaking these tokens down into 32 pieces, each of which is 64 tokens long. We leverage rotary positional embedding, training all our models for 500,000 steps on a TPU v4-64 machine. The effective batch size we use is 131,072 tokens, obtained by raising 2 to the power of 17. For every model we train, we utilize the GPT-Neox tokenizer, which has been trained on a dataset known as the pile and includes all the domains we test on. We use the unique 1.4 billion parameter version of Pythia as our scoring language model. This model scores the top 20 candidates, generated by a ranking algorithm known as BM25. Our model architecture includes 12 layers and has a hidden dimension of 1024. It employs 8 attention heads, each with a dimension of 128. We integrate canonical correlation analysis, CCA, every 2 layers and set 2 neighbors unless specified differently. More details on the implementation can be found in the appendix. In terms of datasets, we test our recursive positional transformer, RPT, model on 4 different ones, which cover various areas like books, code, and mathematical writing. These fields require the model to remember information over long distances. From our data size statistics and document length distribution, we observe that across all datasets, documents are notably long. This is particularly true for 2 datasets, PG19 and Books 3, where the documents typically contain 100,000 tokens or more. Let's take a brief look at the datasets we're using. Section summary. During training, sequences of 16,384 tokens are split into 4 devices, each consuming 4,096 tokens. The model uses rotary positional embedding and is trained for 500K steps on a TPU v4-64, with an effective batch size of 2 to the power of 17 tokens. The model is evaluated on 4 datasets covering domains such as books, code, and mathematical writing, which require the ability to recall information over long distances. Section. PG19. We've used several sources of data in our study. Firstly, we incorporated PG19, which is a well-known benchmark used for long-range language modeling. It is sourced from Project Gutenberg, and therefore, contains a diverse collection of books, varying across many literary genres, styles, and topics. The way we have used this dataset is exactly as previous research has done. Secondly, we've also made use of Books 3. This is a substantial body of books, which is part of the pile. The pile consists of an extensive collection of literary works, spanning across different domains. As far as we know, we're pioneering the use of this body of works as a long-range language modeling benchmark. The third source is CodeParrot. This is a dataset containing cleaned and almost duplicate-free Python code extracted from various GitHub repositories. To effectively model this type of data, it is necessary to comprehend patterns and understand the context over large segments of information. This makes it a fitting candidate for testing our long-range language models. Our experiment utilizes the method previously applied, which involves combining files from the same repository to build a larger corpus. We then divide this corpus into training and testing sets. Finally, we've utilized arXiv. This dataset comprises academic papers taken from arXiv, and they are primarily mathematical texts. These texts require a high level of coherence and often refer back to previously mentioned information over lengthy passages. Previous research has evaluated long-range language models using this dataset, however, they did not make their version of the dataset public. We instead used the processed corpus and data splits that were made available by other researchers. Section Summary. The PG-19 benchmark is a widely used long-range language modeling benchmark that covers a wide range of literary genres, styles, and topics. The Books 3 corpus is a collection of literary works from different domains and is used as a long-range language modeling benchmark for the first time. The CodeParrot corpus is a collection of clean Python code from various GitHub repositories and is a natural candidate for testing long-range language models due to its requirement for understanding patterns and contextualizing information over long distances. Section 5 Experiments. Chapter 5 Experiments. At this point, we delve into experiments aimed at contrasting our recursive pointer transformer, RPT, model with pre-existing work, utilizing our 4 separate datasets. 5.1 Experimental Configuration. We stack up RPT against several established baseline models and oracles for comparison, which include Transformer XL. This is our most basic baseline model, which is essentially a standard transformer decoder stack that uses sliding window attention. In simple terms, we've taken the RPT model and stripped away the retriever component and the cross-correlation analysis (CCA) layers located in the upper decoder. The sliding window attention approach, as detailed in a previous section, can be understood as a variant of the Transformer XL model. Retro. This is a retrieval-augmented model. In this case, we leave out the retriever component and directly feed the top K neighbors retrieved by the BM25 algorithm into the CCA layers of the upper decoder. Concurrent studies have indicated that training retro with the BM25 algorithm significantly outperforms methods that rely on dense retrieval. When training, we utilize the query that includes both the question and target chunks. However, during inference, we only use the question chunk. RPT-Lex. This is a variation of RPT in which the training signal doesn't come from a scoring language model, but is instead driven purely by lexical information, a method similar to the try model. To be more specific, for a given question chunk, the set of positive chunks includes the top 20 chunks that score highest on the BM25 measure when paired with both the question and target chunks. Section Summary. In this section, the authors describe the experimental setup used to compare their proposed model, RPT, to other baselines and oracles on 4 datasets. The baselines include a standard transformer decoder stack with sliding window attention, Transformer XL, a retrieval-augmented model, Retro, and a version of RPT that uses lexical information only, RPT-Lex. During training, the query and target chunk are used, while during inference, only the query chunk is used. Section RPT-Sem. We have used a number of models in our study, each of which we'll explain briefly. The first model we use is a block recurrent transformer, for which we have employed the standard training procedures and configurations as provided by the official implementation. Another model we employ is the memorizing transformer. Again, we use the official version of this model with the recommended configuration. Specifically, this model has a memory capacity of 32,000 tokens, allowing it to hold a substantial amount of information. To get the best results, we have also used something called an oracle during our tests. An oracle is a method that allows us to find the best possible neighbors for a model according to a given scoring language model. By imitating the ranking produced by this oracle, our models can aim to achieve the best possible performance. Our performance evaluation involves a few different metrics. First, we use a measure called perplexity to assess the performance of our models. We also use the target score from our scoring language model to generate a gold ranking for each chunk of data. This gold ranking allows us to label chunks as either positive or negative, based on their target score. We then use these labels to compute 2 other metrics, precision at K and recall at K. Precision at K measures the fraction of the top K ranked chunks that are correctly labeled as positive. On the other hand, recall at K calculates the fraction of positive chunks that are included in the top K. Ranked chunks. Finally, we use our gold ranking to calculate NDCG at K, a commonly used retrieval metric. This helps us evaluate the performance of our models in information retrieval tasks. Section Summary. The section describes the evaluation process for the RPT-Sem model, which is part of the block recurrent transformer. The model is evaluated using perplexity and precision at K, recall at K, and NDCG at K metrics. The evaluation also includes an oracle that exhaustively searches for the best possible neighbors for the model at test time. Section 5.2 Results. The findings in Section 5.2 of our paper reveal that our model, RPT-Sem, consistently performs at least as well as, if not better than, all other baseline models across various datasets. We've noticed that utilizing a fixed retriever such as Retro significantly improves performance when compared to the Transformer XL. However, using the RPT-Lex model resulted in enhanced outcomes in the Books 3 dataset but was less effective in the PG19 dataset compared to Retro. In terms of outperforming the other models, RPT-Sem shines, besting the Transformer XL, Retro, and RPT-Lex on the Archive, PG19, and Books 3 datasets. In addition, RPT-Sem's performance is on par with Retro when tested on the Code Parrot dataset. In comparison to models such as block recurrent transformers and memorizing transformers, which do not employ canonical correlation analysis, CCA, the performance of our model remains either equivalent or superior, showing significant improvements on the Archive, Code Parrot, and Books 3 datasets. A major advantage of CCA is that it allows for a dynamic increase in the number of neighbors at the time of inference. Thus, when we increased the neighbors to 3 or 4, up from 2, we noticed an enhancement in the model's performance. This indicates that it is possible to sacrifice some computational efficiency in exchange for improved performance. Lastly, the so-called oracle models consistently delivered the best perplexity results across all datasets. These showed improvements from 2.74 to 2.69 on the Archive dataset, from 2.15 to 2.10 on Code Parrot, from 10.92 to 10.26 on PG19, and from 13.87 to 12.74 for Books 3. These results indicate that by refining the training of the retriever, it's possible to further boost the overall performance of the model. Section Summary. The results show that RPT-Sem outperforms other baselines, including Transformer XL, Retro, and RPT-Lex, on Archive, PG19, and Books 3, and has comparable performance to Retro on Code Parrot. The use of CCA allows for dynamic increase in the number of neighbors at inference time, resulting in improved performance. Additionally, oracle models consistently achieve the best perplexity across all datasets, indicating that improving the training of the retriever can further improve performance. Section Retrieval Metrics. Metrics for retrieval *. The table provided shows various retrieval metrics with reference to optimal positive chunks. The retrieval procedure employing RPT-Sem significantly outperforms both RPT-Lex and BM25 in all scenarios. This underlines the crucial role of a well-trained retrieval system and furthermore highlights how semantic supervision enhances retrieval performance when compared to merely using a lexical signal. Distribution of improvements over chunks *. We've determined the improvement in perplexity, a measure of uncertainty, for all chunks, by comparing with the Transformer XL model. The distribution of these improvements is then plotted for Retro, RPT-Lex, and RPT-Sem. Evidently, RPT-Sem boasts a more pronounced right tail in all scenarios with the exception of Code Parrot, thus signifying its advantage over other baseline models. In the later section, we delve deeper into why Retro combined with BM25 performs well on Code Parrot. Ablations. Section 5.3**. The results of a dedicated ablation study conducted on RPT-Sem over all datasets are showcased in the given table. Here, we've implemented a condition known as only teacher forcing. In this situation, we direct the model to pay attention exclusively to the top-ranking neighbors according to the scoring language model. Importantly, the probability associated with the text, denoted as P_text SS, isn't gradually reduced during training. This tactic results in a performance decrease across all datasets, and it's especially noticeable for PG19 and Books 3. Section Summary. The retrieval metrics in table show that RPT-Sem outperforms RPT-Lex and BM25 in all cases, indicating the importance of training a retriever and using semantic supervision for better retrieval. The distribution of improvements in perplexity for all chunks also shows that RPT-Sem has a heavier right tail, further illustrating its advantage over other baselines. An ablation study on RPT-Sem over all datasets in tab shows that forcing the model to attend to gold neighbors without annealing P_text SS during training leads to a performance drop across all datasets, particularly for PG-19 and Books 3. Section: No teacher forcing. In the approach called no teacher forcing, we choose a slightly different path by keeping the probability of sampling from the source text, denoted by p_text ss, at 0 during the entire training process. This implies that we exclusively rely on our model's predictions for determining neighboring elements, and we refrain from using any correct or gold ones. However, this approach has a downside. It can lead to our canonical correlation analysis (CCA) layers being undertrained because they are initially exposed to neighbors of lower quality. As a result, the performance falls even more when compared to the only teacher forcing method. Next, we tried turning off the feature known as neighbor gating, which helps to regulate the influx of information from neighboring chunks. When studying the impact of this change on our model's performance, we noticed a drop in all datasets, particularly on Books 3, where perplexity grew by 4.5 points. It's important to note that the neighbor gating function works independently from the type of retriever used. To illustrate this, we added neighbor gating to the retro system and shared the results, which yielded mixed outcomes. Another aspect we examined was token overlap. In figure, it illustrates the average number of tokens that coincide between the query and target chunks and the top retrieved neighbor for 3 models: Retro, RPT-Lex, and RPT-Sem. It was observed that RPT-Sem fetched paraphrases that had a higher overlap with the target chunk compared to RPT-Lex. As expected, the BM25 model retrieved chunks that were most similar to the query chunk. However, this didn't necessarily lead to an increased lexical overlap for the target chunk. Section summary. The paper explores the impact of different training methods on the performance of the CCA layers in retro. Fixing p_text ss equals 0 throughout training leads to undertraining of the CCA layers, resulting in a drop in performance. Disabling neighbor gating also reduces performance across all datasets. RPT-Sem retrieves paraphrases with higher token overlap with the target chunk compared to RPT-Lex, while BM25 retrieves chunks with the highest overlap with the query chunk but not necessarily with the target chunk. Section: Supervision quality. The quality of guidance or supervision during the training of our model, RPT-Sem, significantly contributes to its enhanced performance. The training is dependent on information from the so-called target scoring function, which enables a reorganization or re-ranking of the top 20 candidates based on the BM25 ranking algorithm. This natural question arises: to what extent does this re-ranking process improve the quality of supervision? To answer this, we present a figure that illustrates the highest target score within the top K chunks, as determined by BM25. This score is calculated as an average across all chunks and our 4 distinct datasets. The evidence shows that there's substantial potential in re-ranking the top 20 BM25 candidates. This is because the highest target score is significantly greater for the top 20 candidates compared to just the top 2. This finding implies that we can further enhance the RPT-Sem's performance with more comprehensive and better quality training. Our data analysis offers an interesting perspective on why our model, RPT-Sem, noticeably outperforms the retro model on the datasets Books 3 and PG-19, but not so much on CodeParrot. The maximum target score for CodeParrot at K equals 2 is already fairly high, around 0.1. This value corresponds to an over 10% increase in the likelihood of the target chunk compared to the local context. In contrast, for the datasets PG-19 and Books 3, the target score when K equals 2 is much closer to 0. This suggests that for CodeParrot, the use of lexical information or word-based data alone is quite effective. This could potentially be due to the retrieval of function definitions, variable assignments, and similar elements, indicating that the type of information being processed can significantly impact the model's effectiveness. Section summary. The RPT-Sem model is trained using information from the target scoring function s_t, CDOT, which improves the model. Re-ranking the top 20 BM25 candidates has a lot of potential, as the maximal target score is much higher for the top 20 candidates compared to the top 2, indicating that longer and better training of the retriever can further improve the performance of RPT-Sem. The analysis also suggests that lexical information alone is quite effective for CodeParrot, potentially by retrieving function definitions, variable assignments, etc. Section: Subgroup analysis. Let's delve into a subgroup analysis. What you'll see in the included figure is the average relative improvement of 3 distinct methods: Retro, RPT-Lex, and RPT-Sem, as they are compared to Transformer XL. We specifically look at 2 scenarios here, one where an optimal gold chunk was successfully retrieved, and the other where no such gold chunk could be found. As anticipated, RPT-Sem uplifts performance on all datasets, beating all competitors except for Retro. Interestingly, Retro holds its own, delivering similar performance as RPT-Sem on code parrot. We also noticed that situations where a gold chunk was identified led to larger performance boosts. However, the surprising part was that improvements were still observed even when no gold chunk was found. This indicates that the model can still profit from these non-gold retrievals. Now, let's shift our focus to long-range language modeling. This is an area where the crux of the matter is dealing with the quadratic complexity of attention mechanisms to manage longer texts more efficiently. For example, Transformer XL is an approach that processes input using a segment-level mechanism, and it also stores a cache from earlier segments for later use. A model called Longformer takes this concept a notch further, to handle even larger chunks of context. There are also sparse strategies, which only pay attention to a select subset of tokens using clustering or hashing methods. Another method in practice involves compacting the input and attending to this compressed sequence, or learning to disregard tokens that aren't relevant to the task at hand. Lately, we've seen a resurgence in potential solutions using recurrent mechanisms. From an analytical point of view, previous research has shown that traditional language modeling benchmarks don't perfectly measure a model's ability to handle long-range contexts. We discuss the different types of sequences that benefit from extended context and explore the impact of various long-range architectural choices. We recommend enhancing the long-range capabilities of the upper layers of these models. Section Summary. The section discusses the performance of Retro, RPT-Lex, and RPT-Sem compared to Transformer XL and distinguishing between cases where a gold oracle chunk was retrieved and cases where no gold chunk was retrieved. RPT-Sem leads to improvements on all datasets and even in cases where a gold chunk was not retrieved, showing that the model can still benefit from such retrievals. The section also explores various strategies for long-range language modeling, including sparse strategies, compressing the input, and recurrent mechanisms, and recommends increasing long-range capabilities in the upper layers. Section. Retrieval-Augmented LMs. Retrieval-Augmented Language Models, or LMs, have emerged as a potent tool for harnessing external knowledge while creating text. These models can be categorized into two types based on their level of operation: token level and sequence level. Token level models, such as KNNLM, TRIME, and SPALM, extract information for individual units of text, also known as tokens. On the other hand, sequence-level models, such as RAG, use pre-trained encoder-decoder models in combination with pre-trained retrievers for tasks like open-domain question answering. FID, for instance, uses generative encoder-decoder models to amalgamate information from multiple passages during the decoding process. This method is closely linked with the CCA mechanism. A recent advancement has shown the potential benefits of carrying out retrieval and chunked cross-attention at each step. This is a departure from the original Retro paper's approach, which conducts retrieval every 64 steps. Next, let's discuss joint retriever-reader training. Joint training methods primarily focus on transferring information from a pre-trained reader to a pre-trained retriever. These strategies often involve updating the retriever's index during training in knowledge-intensive tasks, such as open-domain question answering. For example, Realm uses masked language modeling to refresh the retriever's index. EMDR2 improves on FID by using encoder-decoder models to trace back errors from the predicted answer to the retriever. Moreover, it has been shown that it is feasible to use attention scores from the reader to guide the retriever. Significantly, there have been attempts to further scale up these strategies and jointly train a retriever with an encoder-decoder model, exhibiting impressive few-shot learning capabilities. There's also exploration around different retriever updating techniques to manage any discrepancies between the training and testing stages of the retrieval process. In our work, we avoid the issue of index update, as we compute the entire index in a single forward pass. Section Summary. Retrieval-Augmented Language Models, LMs, are effective in leveraging external knowledge while generating text. These models can operate at token-level granularity, such as KNNLM, TRIME, and SPALM, or at sequence-level granularity, such as RAG and FID. Joint retriever-reader training approaches transfer information between pre-trained readers and retrievers, with methods like Realm, EMDR2, and attention scores from the reader used to supervise the retriever. Recent studies have scaled up these approaches and jointly trained a retriever with an encoder-decoder model, demonstrating strong few-shot learning capabilities.